Hello, everybody, and welcome to the next session in the J Champions Conference. I'm Geert-Jan. I'm active on Fujay.io, the place for friends of OpenJDK, and I also work at Azul. And I would like to introduce to you my friend Bazlur from the Bangladesh Java user group, and who is also very involved with complicated topics in the Java ecosystem, and especially when you're beginning, and even when you're more advanced in Java. And so this is also the topic for today, a tale of two cities, how blocking calls are treated. So I'm going to hand you over right away to Bazlur to take away this concurrency topic.
Thank you very much for the introduction. All right, folks, let's start with this talk. Welcome, first of all. And as you can see, the title of this talk is Two Cities, How Blocking Calls Are Treated. I come up with the idea is, blocking operation is treated differently in many places. So that's how I basically came up with the fancy word, which is Tale of Two Cities. It's interesting, and it's when someone sees this title, they get intrigued. So that's why the catchy name. Ultimately, I'll talk about a bit of history of Java concurrency related to the blocking operation, obviously, and I hope you like it. And who doesn't like a bit of history? All right. I'm going to move on to the next slide. Let's see if I can. Yes. John already introduced me, so I'm gonna skip this. Only one thing that I would like to tell you, which is I love writing. So if you want to read my content, you can definitely go visit fuje.io. Apart from that, you can also find my content on InfoQ and Dijon. All right, moving on. So first of all, let me put forward the agenda first, right? As I said, so this will be a bit of history rundown. I'll probably not go in depth on a particular topic. Once you know the highlight, you can always look up and figure the rest. So I'm sure you are smart. All right. So I'll start with a bit of context, the history stuff, and then share how blocking and non-blocking operations are done. What are the alternatives? And I'll try to touch a bit on computable future reactive stream, and then finally I'll focus a bit of time on Project Loom, which is the new thing, the greatest thing in Java ecosystem. So yeah, I'm sure you're gonna like it, or at least in um, if you are I mean, this Project Loom is here for we have been talking about this for a long time, so you're already familiar with that. So in that regard, if I make any mistake, correct me, that way I'll learn. All right. So moving on. All right. So we all know that Java has been around over 2 decades, right? It has been, and I believe continues to be, dominant force in software industry ever since, right? There are multiple reasons why it is doing so well. One of which is definitely concurrency, right? So Java started its journey by introducing an inbuilt threading model. Basically, you can say threads are the way of expressing concurrency in Java. Like this statement over here, from the day zero Java introduced threads. It's very true. We can say threads are the basic unit of execution in Java, and any Java code we want to run is executed by a thread. We can draw that conclusion that threads are or we can say, or differently, threads are an independent unit of execution environment of the Java platform. From this, it is easy to see that a program with more threads has more place to more place where it can run code, right? So that's amazing. And in fact, threads are in all layer of Java platform. It could be exceptions, it could be local thread locals, debugger, profilers. The threads execute codes in and let's say we call a method, it calls another method, it calls another method. That's why we create stack trace, right? So threads keep those stack trace. So that's how we get to know about call stack. Beside, we use thread if we want to debug our program, right? Or through an IDE or some other ways. If we need to profile a particular part of Java applications, we also use threads. All of this point out that concurrency or threads, whatever you can call it, for now it's fine. Is an integral part of programming platform in Java. So that's the history. All right. So moving on. Now let's know a little bit about how we create threads, basically, right? So we create instance of threads like this, new threads, and then inside we provide a runnable interface or Lambda expression. Nowadays we're going to obviously use Lambda expression, since Java it is a long ago. Java is released a long ago, so we are pretty familiar with Lambda expression. So I'm not gonna talk about runnable interface anymore. Anyway, so this is how we create threads. Even though sometimes threads are creating threads like this are hidden because we use different set of APIs, but fundamentally the way of creating thread is like that. We instantly create of new threads. All right. So that's a basic. So now we have to keep in mind that Java threads are basically OS threads. That means when we create instance of java.lang.threads, it's just a thin layer. That means OS control threading, OS control scheduling. We just ask OS to get us a thread. So that's it. So we have to keep that in mind. All right, moving on. So now the question gets to be, where do we mostly use threads nowadays? A common answer would be obviously web application, Java web application, because that's where Java is most popular. There are other places, definitely. Java is general purpose language, and we can do pretty much anything with Java. But let's focus on one thing at a time. So let's think about a web applications now. So in modern web applications, we care about throughputs, right? Throughputs, what does it mean? It means a web applications refers to a number of requests that can handle by application in a given period, typically measured in a request per second, although, right? So from that we can derive that throughput is achieved by concurrent connection. So if you have more concurrent connection in a particular period of time, that means we have more throughputs. So usually a dedicated threads is given to every request from a client. Modern operating system in fact can handle millions of concurrent connection. This indicates that we will have more throughput if we have more concurrent connection. This conclusion may seem legitimate, right? However, the reality is a bit far from it, right? The reason is that we cannot create as many threads we want to create. So threads are essentially limited. Okay. Not only threads are limited, threads are also expensive. For example, creating a thread takes about 2 megabyte of memory outside of the heap. We must also remember that traditionally Java threads are like thin wrapper. I already told you about that. And it's basically operating system thread, and we can only create a few of them. Even though we can get a good amount of it, but we cannot always guarantee if we create a lot, with the the overall performance of application. We can guarantee that. Also, there is a context switching. You can test uh, you can test by a code for in your local machine. For example, how many thread you can create. I have a code over here. I will show you in a minute. For example, that's the code. So what I did is I tried to create as many thread I can create on my local machine, and I end up creating around 16,000. Okay, so I have a good machine. That's why. But usually, the machine that we run on application probably will not have that much. Will not be able to create that much threads. Also, even we can create a lot of threads. That means our operating system is always busy with context switching. That's also going to hurt the performance of application. So that's what I was telling earlier. So once we keep creating, and then we'll end up something like this red line over here, which is out of memory error. So that's a problem. That's a bummer. So we can have a lot of threads. I just wanted to remember that. Keep remember all this information. It's in history. So anyway, moving on. So now let's go ahead with the next step, which is what problem do we have now? I mean, we have we can create a lot of threads, and threads have ability to give us throughputs, and we can independently run code inside a program. So we can do a lot of things. But again, although we have limitations in number, but we are good. We have been doing just fine last 20 years, right? But what problem we are facing now? So that's the question we're going to ask now, which is so let's see some facts first. So for the facts, it's modern applications development require high scale, right? A high data scale, as we need to deal with too much data. I mean, we are producing a lot of data nowadays. We have high uses as well. That brings us to a cost associated with it, right? Cloud computing cost can quickly accumulate it if we're not careful. Um, you know, Also, we have established that creating threads is not cheap, and they are limited in number, so we cannot afford to waste any of them, right? If we create one, we want to utilize whole thing. Um, so so basically what it means that we need to use their full capacity. However, that's not what happened in reality. And the traditional programming model blocks the a lot of threads. Basically, we get to waste a lot of threads. In how, I'm going to show you in a minute. So when, for example, when we call something that take time to respond. For example, if we make a network call, let's say I have a microservice calling another microservice to get a data or database call. The thread we are using to invoke that call gets blocked until we get the result. So that's a problem, right? So while we are waiting for the result, the thread does nothing. It just sit idles, and it just wastage of valuable resource, resulting in cloud builds that has no good reason. So that's the problem. Basically, we don't want to waste our resources because we have a limited number of resources, and if they stay idle a lot of time, that's definitely we are paying for no good reason. All right, so we established the problem. Now, this is the typical scenario of web application. So I'm going to skip it. Basically, we get request. Each request get a thread, and this thread basically calls other things. It could be database, it could be microservice. Until you get result, it just blocked. So it's a visualization of typical web application. Anyway, moving on. Now let's see an example, a real example, how traditionally we do. So in this code, we make 5 method invocations, right? Like get person, they get the person information, then get asset, and then we get the liabilities of that person. And meanwhile, after all of those doing this, we need to do another something important task that's also takes some time. And then after all of those invocation, we calculate the credit of that particular that person. So basically this method does calculate credit for a person. And it basically one method call result, five invocation, five method call. Let's assume all of them require some time to process. Obviously, it could be, for example, get person can go into database, get asset also going to end up with a database call, or it could be another microservices. We never know. Just for the sake of argument, it takes, let's assume it takes 20 milliseconds to process each subsequent call. So since we are making all the calls, one after one, so we'll require at least 1,000 milliseconds to complete these whole methods, right? Therefore, the thread that started this first invocation, which is calculate a credit for person, must wait to finish them, finish all of them. From this scenario, we can see that the threads that invokes the calculate credit for person method is blocked most of the time, because it just invoke and then wait to get result. While it's blocked, it's doing nothing. So it's a resource are being wasted by not being able to do anything. Now the question is, how can we improve it? Is there any way to improve this waiting wastage? Well, yes. Last few years, I mean last 20 years, we have made several attempts to improve the situation so that thread don't get blocked, or at least we can improve a bit. So for example, it takes 1,000 milliseconds plus. Maybe if we can reduce it a bit, it's definitely improvement. So we'll go through that journey, how we started and how we end up. So moving on, so like over here, all of them are pretty much parallel, right? I'm just giving you a cartoon picture over here. The invocation inside the method of the earlier slides code are not all dependent to each other, right? Some of them, for example, the second, third, and fourth invocation can be done parallel. This one, and this one, and this one, they can be done parallel. So if these three methods gets executed in parallel, we can make some improvement. The invoker thread would then take less time, which means less blocking time. That's a huge improvement, I would say. Now the question gets to be how we are going to do that. So that's where we're going to go in the next slides. So the idea is some of them are doing work parallelly. So end result is all of them are going to get we're going to get result from all of them, but it will take less time because they are doing parallelly. Anyway, moving on. So there is a classical implementation, which is we used to do back in the day. It's not, we don't do any of those now, but I just wanted to give a history. So this is how we used to do earlier. And so the idea is we're going to start a new thread, and inside thread we are going to fetch the get person, because when we call threads, threads are independent, right? So if we have a new we have a 5 threads inside a method block, they are going to start independently. And once the data is arrived, we have to store in a atomic references so that we don't the data doesn't get stale. So if we use this classical implementation, we end up like this above code. So basically, we're going to get first person, and then we're going to get atomic references, and we'll create T1, which is thread 1, T2, thread 2, T3, and we're going to start all of them. And we have to join because we need the result and to calculate the credit. And finally, we're going to calculate the credit, which is can be, and then we're going to join, and then wait for the result and return the credit. So the idea is, if we keep this definitely improve a lot. The overall time of this calculate credit in person reduce. The problem is that there is some problem over here. I hope you if you don't if you see that, right. Let me explain a bit. So the problem is we cannot control how many threads we are going to create, because we know that threads are limited, right? So if we have a lot of requests, so we're going to continue creating new threads each request. So we don't have any control. If we keep creating threads on an ad hoc basis, we may end up creating too many. So that's end up the red flag we shared in the earlier slides, which is out of memory. All those problem can come, right? And also, if we have too much threads on an application, it's going to do a lot of context switching, so that's going to hurt our applications overall. So we need to improve further. The idea is we need a control mechanism. That means we want to create this amount of thread, not more than that. So that's where basically Java 5 introduced executors, and it introduced future, runnable, callable. It gives us control how many threads we want to create. So it gives us a way of creating pool. All right. So what we can do is we will create an executor, executor service. With this executor service, we create a pool of threads. We can put a number. How we're going to come up with the number, that's a different question. That's another discussion. But overall, you can try and this is the sweet spot. You can figure out it's different from different applications. So you have to figure out that sweet spot for yourself, based on the requirement, based in the criteria of your application. So, but yeah, it can be varied. But idea is, let's say you have a executor of pool executors, which is essentially a thread pool, and let's say you create 100 threads. So all of those 100 threads will decide, and you can send requests to those 100 threads, and only 100 threads are going to use to work on your task. That way we are basically getting control over the number of thread we can create. That's definitely a huge improvement. So all right. So yeah, I mean, we have been doing this way for several years, and we have definitely got so there is a question: can't we use executor service? Yeah, that's what I'm talking about. Yeah, the executor service is basically the huge improvement compared to the classical implementation. So that's what we're going to use over here. So let me show you the picture how basically executors works. Essentially, you have a thread pools, and that's your main thread. Let's say from here, you are going to send a request. Basically, you will send a task to the thread pool, and there are a lot of threads waiting. So we are going to send those tasks into your blocking queue. A thread pool usually maintain a blocking queue. So you are putting all your tasks to the blocking queue. So when you send a request, immediately it gives you a reference, which is future, and you can hold on to that future and send other requests. So so the idea is all these threads in this thread pool keep pulling tasks from this blocking queue, and keep executing them. So they're always busy, essentially. All right. So that's essentially thread pool from the very high level works. Anyway, so moving on. Now the questions gets to be: are we there? Are we? Where basically did we solve the issue? Yes, we made a lot of improvements, but the future mechanism that it offers is still quite low level, right? It's quite complex. The get method is also blocking call, although we are making asynchronous calls. In the end, we need to block to get the data from that thread if we want to call this get method, basically, essentially. So there are other problems associated with it. So I'm going to skip those problems for this slide because I have a few other stuff to share. I'm going to skip some of this stuff for the sake of time. But yeah, I mean, I'm going to share the slides with you. So if you are interested, you can look them later. Anyway, the bottom line is we made a lot of improvements, but we are not there yet. So so let's improve a bit more, which is Java 7 introduced fork join pull. It's another implementation of executor service, but it's a better implementation. It solved a lot of problems that we had earlier. So the one of the thing it's understand that let's say we are in the fork join pool. Let's say we have 8 thread in the pool. Each of those 8 thread will have their own queue. So 8 of them are going to have their own queue. So you are going to send a task. The idea is that I'm working on this particular task. The data that I'm working with, yeah, the next task also going to probably use the similar kind of data. So we don't have to reload data from different locations. So that will improve some of the there is a concept called cache corruption. If we loaded data to a cache, CPU cache, and then another thread removes it and add another data, so that also lose some of the time. So the fork join tool is going to prevent that cache corruption, and also it's use localization. That means let's say we have a 8 core machine in our computer. So and let's say we have 8 threads. So the thread that running on a particular core is going to keep running on that particular core. So it's a better implementation in nutshell. Anyway, here is some descriptions that you can read later. So moving on. All right. So obviously we improved a lot since Java 7, but Java 8 introduced computable features, which is even awesome. We can do a lot of composability. We can chain. We can do functional programming with this. So that's an amazing, and it is built on top of the previous idea, which is fork join pull. So moving on, if we use the fork join computable feature, it looks like this. Similar thing, but we can change things over here, and we can use fork join pull by default if we don't provide any. So there will be a common pool in JDK. We can use that, or we can create our own. That's up to us based on the requirement. We're not gonna go into that in this discussion, but yeah, this is the final outcome we can get. So this is also improvement. We can do functional style of programming. We can use computable features, and it's quite improvement. And computable feature is a quite big class. It has like more than 3,000 lines of code. It has a lot of helper methods. For example, it has like more than 50 methods we can readily use and pretty much serve all our purpose. And a lot of tasks can be combined. You can think computable features. It's a box. It's a mystery box. You can put your stuff, and as long as the stuff inside that box, they are going to however you can change. You can run if you want to run them asynchronously. If it's inside the computable feature, inside the box, it will run asynchronously. So and we get all those benefits. Anyway, so now the questions gets to be, well, so far we have done great. We had a classical implementation. We moved to the executors, and then fork join pulls, and then computable features. Were there any other alternative out there? All that we had, right? Like we have gotten everything we wanted. We improved performance and composability. However, there are some alternatives in this market. For example, reactive frameworks, ArcJava, Akka, Vertex, they are also doing great. So also they are giving all these benefits, which is performance, composability benefit, and I'm gonna show you show you a code. This exact same thing can be done with Webflux, which is Spring offering. So let's see how it looks. So this is what it looks like in a Spring. So this is using the Reactor framework. The idea is we're going to get the similar benefits, same benefits, but we have to write our code in a different fashion. So that's the idea over here. I'm trying to put all of those things and I tried to get the same result, and it's reduced the time of calculating credits compared to others, but it's just different. So now the question gets to be, what are the drawbacks of having reactive framework, right? I mean, we had other alternatives. We have multiple alternatives, but why we are keep moving from one place to another? There has to be some limitations or drawback. One definitely is learning curve. Learning reactive framework is not easy. You have to put some time, and you have to try to understand the concept of it. It takes time. Some of the pattern may seem mind-bending to the beginning. It's a controversial word. I should not have said that. Some of you might reject that. Anyway, but it's definitely a cognitive load associated with this. That's true. It takes some time to learn, get familiar with this. And it's also reduced, I would say it's my experience, it reduced some code reading experience, because as you can see over here, it's doing a lot of chaining. It goes from one place to one place. So from just first reading, it's not that easy to figure out what's going on over here. So that's definitely um, uh, I would say the experience of reading code is not pleasant as the other example I have shared with you. So also there is a thing called debugging, which is extremely difficult. For example, if we run a code inside one thread, it's easier to debug, right? But in reactive programming, you never know which part of the code is running by which thread. I mean, for example, you start with one thread, and then you can get a callback, because internally it's used a lot of callbacks, right? So it can end up in another thread. So you lose the stack trace and all those interesting stuff that we care about. And if you take the thread dump, it's probably not going to be that helpful as well. And also it's easy to overcomplicate things with this. So the questions gets to be, we had a solution, we have everything we wanted, but it has some drawback, definitely. So it's 2022 and 23. We need to find a different way of doing all of those things, right? If not just for sake of different, some definitely we want to some benefits out of it. We want to improve a bit more. So that's where basically Project Loom comes. The idea of Project Loom is it allows us to create as many threads we want to create on an ad hoc basis, and the penalty is the penalty we had for creating a lot of threads are not here. So that's a huge benefit. We don't want to care how many threads we want to create. We just want to create ad hoc basis, and they are pretty much cheap. On top of that, we want to create we want to write some of the code in an imperative fashion, so that it's easier to read, reason about, debug, all those things. So And the other thing is blocking is essentially a problem, right? That's what we are discussing so far from the beginning of the talk. So, and we want to write blocking code without having the problem of blocking code. That's the whole idea of Project Loom in nutshell. So yeah, Java 9 brings a virtual thread with the Project Loom, and we can have, the idea is we can have as much as blocking code as we want, but we are not probably going to have the penalty that we used to have. So yeah, that's amazing, and that's where Project Loom comes. So let's see how it does things. Anyway, so basically, that's the highlight of Project Looms. So it allows us to create millions of cheap, lightweight virtual threads, and each all of those virtual threads can be blocked. And when it's blocked, it's just blocked, but it's not using a consuming CPU. How? I'm gonna talk about in a minute. So now that we have a new kind of threads, that means we had classical threads. We're not removing all of those things. We're still going to use them. We're still going to be a part of JDK. So we have to divide these two threads, right? So one is we can call it classical thread or real native threads or platform threads. There are multiple names. And the other new kind of threads that we are going to have with this virtual Project Loom, which is called virtual threads, or you can call them user threads. So anything that is not virtual thread or user thread are basically classical threads, or you can call platform threads, career threads. The reason career I'm going to explain in a minute. But yeah, so there's two kind of threads now in JDK since JDK 19. One thing you have to keep in mind that is it's not yet out. It's under enable preview. So if you want to try out virtual threads, definitely you have to use enable preview. I'm going to show you the demo in a second. All right. So before going into into all of those things, I'm going to quickly show you a demo so that know how to create a virtual thread. So essentially, creating virtual thread is pretty similar to creating regular threads, but it has a few fancy factory method. I would say builder method. Yeah, it's come from thread builder. So thread dot of virtual and call or dot start, and then you can pass your lambda expression over here, which is essentially a runnable implementation of runnable interface, and then you can run it. You will see the result. So let's run it and see if I can show you the output. Okay, so over here, that's the output essentially. Basically, hello world running from virtual thread. Skip this part for a minute for now. Just read this part, which is virtual thread. That means we ran this line, which is line number 7, using virtual thread. So there are a couple of ways to create virtual threads, which is threads start virtual threads. You can immediately want to start, right? If your virtual thread, then you can use this start virtual thread. It will just it will create and start virtual thread, and it will definitely give you a reference as well if you want to. So all right. And if you want to create a virtual thread and you don't want to start them immediately, so that means you just want to create them and hold on to the reference, and you will run them later. So you can do something like of virtual unstarted. So which means you will pass the task over here, and it will give a reference, obviously. And this unstarted basically a reference of thread which hasn't started yet. So that's the idea. Okay. So now that we have a fancy builder pattern over here in the thread, why not we have, if you want to create the classical threads, which is essentially our old generation of threads. If you want to create them, how we're gonna create them? So we can create them using off-platform methods. So they have added this so that we it has the similar kind of way of creating threads, and you can create you can create start and started method both. So if you want to create if you call this start method, it will start immediately, and if you want to hold on to the reference and start later, you can call this unstarted method. Just I wanted to show you that we have this available now since Java 19, and we have to keep in mind that this is also under enable preview. So preview feature. So if you want to use this, definitely you have to pass the enable preview flag. Hopefully someday we're gonna get a better I mean, they're going to be a part of JDK definitely, and enable preview is going to be go away. We're waiting for that, but for now you can also try out and see the result. So there is a question. Let's see if I can answer immediately. In the Loom talk with Mario Sko, that it be take 5 years for Loom to overtake reactive programming. Do you agree? I agree with that, definitely. I mean, reactive step is also a solid programming model. It's been here for a long time, right? We have built a lot of product already on the reactive stack, so we are not gonna throw them away tomorrow, first of all. And also, reactive stack also solved some of the other problem that the Project Loom didn't touch yet. I'm not sure if they're gonna do that. So, for example, one of the thing is, I forgot the term. Mm, back pressure, for example, right? Reactive, you can do that using reactive programming, but in Project Loom, we are not even there to do all those things. So we can achieve those things in different ways programmatically, definitely, but it's not straightforward like call a method called back pressure and it will automatically do the back pressure. So definitely reactive programming is not going to go away tomorrow. It has a lot of potential and it's going to stay there. I mean, in programming in general, there are a lot of programming model that's old. We know that has some problems, but we still use them right nowadays, even though we have a better alternative. So they're going to stay there, and they're going to solve a different set of problems. So I completely agree with that. It will take time, and things, especially, some of the things that comes to JDK are taken, takes time to get used to by all of the industry, right? So it will take some time, for obviously. But for the long run, like next 10 years, probably the popularity of reactive programming is definitely going to reduce. That's something I can share with you, obviously. But yeah, but I'm in general, I'm definitely excited about the Project Loop. For example, if Project Loop comes to in the next JDK distribution, and I'm gonna use, I'll try to use them in my code. So probably not reactive programming immediately, and since it has some other associated problems that I already discussed. That's my perspective, but someone other in some other teams, some other companies, they will probably use reactive programming because they have been learning reactive programming for a long time, and they have they have this knowledge with them. So they're gonna definitely use that. So yeah, so in nutshell, the answer is yeah, it will take some time to overthrow reactive programming, and probably it will not. Some of the company is going to continue use the reactive programming for long run. Anyway, sorry, it took a while to answer these questions. So moving on. So I've just showed the demo, so I'm going to skip these slides. And the idea is, if you want to use virtual thread in JDK 19, you have to enable preview feature, and these are the ways you can enable virtual threads if you want to use. And there's also, you can use tryout in JShell as well. So that's interesting. Okay, moving on. So I'm gonna show you a quick demo how it essentially works. So I'm gonna gloss. Uh, I'm gonna gloss over it because it's definitely begs in a whole discussion, or maybe a whole presentations, how continuation works, how schedule works. So since we don't have much time, so I'm gonna just gloss over a bit. So give you a context how it works essentially. How come we can create virtual threads a lot cheaper, and how come if we want to block certain things, it's just cheap. So that's where we're going to show you a example, which is called a concept called continuation. And there is a scheduler, uh, basically. So the highlight is there's a thing called continuation. I'm going to show you in a minute, but highlight is from the very bottom, high level. Virtual thread is basically a Java construct, right? It's like a Java classes, Java object, and there would be a career thread, which is basically our classical thread. Let's say I have a classical threads inside a proc join pool. Let's say this is my classical threads, and inside classical threads I'm going to send a virtual thread. Virtual thread is basically a Java class, Java construct, looks like thread. It's we're, as a developer, when we're going to run code, we're going to treat virtual thread as a thread, regular thread. All the functionality is going to be the same, but inside the JDK, it's a Java construct. The operating system doesn't know, or will never know about virtual thread. So that's the distinction, internal distinction. So there will be a career thread. Let's say this is my career thread or traditional native thread. I'm going to pass a virtual thread over here inside this career thread. So this career thread is going to execute my code that I put inside the virtual thread, and if this virtual thread, while executing, see any blocking call, let's say it's a network call, it's a sleep method, what it will do is it will resume from the execution. Uh, it will so not the resume, it will just yield itself, so that the career thread is now free to execute another virtual thread. So let's say I have a long list of virtual thread, and this is one career thread over here. And So I'm constantly sending virtual thread, and the career thread is executing one virtual thread at a moment, at a point of time. And if it sees any blocking calls, it will yield itself until it gets the result, right? So now the career thread that's running virtual thread is free, and now it can take another virtual thread to continue the executions. So in my computer, in my application, let's say I have a fork join pool, and fork join pool has like 19 or 20 career threads, and this 10 or 19 or 20, whatever the number, is always going to run virtual threads. And I have a million virtual threads, so all of them are come to the career threads or inside the fork join pool. And fork join pool basically schedule, and while executing a virtual thread, if it sees a blocking call, it will just yield itself, and it will the career thread is available again, so it will not waste. So it will continue executing another virtual threads, while the virtual thread that is suspended is waiting. It's inside the heap, it's inside the memory, but it's not consuming or consuming any native thread or any threads. Basically, it's just outside of the scope of thread. So it's there, but it just occupying the memory, not the resource, not the CPU. So that's what essentially happens inside virtual thread. So even though we have millions of them, million objects can reside in the Java heap, right? They're there. If all of them are blocked, they are fine. They are not continuing or consuming our valuable resource, which is CPU time. CPU is always busy executing other things continuously. While if I have a virtual thread which is blocked, it just blocked outside of the scope of running, my what do we call native threads, right? So that's essentially highlights. So that's why it is cheap. We can create a lot of them. If we want to block, we can block. It will just move away from executing. So the thread that it's executing, it's not going to be waiting or in sitting idle. So if I have a few number of native threads or carrier threads or classic threads, it can execute a millions of virtual threads. Essentially, that's how it works. Hopefully, I can give you a quick demo of continuation if I have. Let's see if I can do that. So this is so essentially when we create a virtual thread, and if we put some code or implementation of runnable interface, or let's call it a task. A runnable is basically a task. So if I put a task to a virtual thread, inside creates a continuation scope, and it also create a constant continuation class. It's an internal class. As a developer, we are not supposed to see that class, or we're not supposed to use that class. So we probably won't able to use continuation because it's a JDK internal class. But I can, what I can do is I can do a demo using supplying this flag. So ideally, we are not going to do that in production or any of serious code. It's just for sake of the demo. So what happens is, just look at this line number, this 3 line basically. So you can call it, it's an implementation of runnable interface, right? It's a Lambda expression basically. Equivalent is basically a runnable or task. So over here, the first line, we're executing the first line. The idea is when a thread is going to execute this 3 line, they're going to execute one by one serially, particular one thread. So if I go over here, it will execute first line, and then second line, and then third line. If somehow we get interrupted over here, it will come again from the beginning. That's the idea, traditional idea. So we have created a continuation over here, and it just object of continuation. So when we call this continuation dot run, it start running this line basically. And now we're going to call this system.println start, just to show you that we have started running the continuation, and then call continuation.run. What would happen is over here we see continuation.yield. So this line is basically yield the executions. So if a thread is basically, let's say it's a part of a virtual thread, and it's running something, and it ran the first line, and then it sees a yield operation. So it will just suspend the executions, and the execution will suspended from here. So in the virtual thread, when the API of JDK was overhauled, they changed a lot of API. For example, a lot of IO classes has been changed in favor of this Project Loom. So if there is they see a call or invocation, something like that, it's going to be blocked, they called something like continuation.yield. So let's see a demo. The idea is it will first call this C1, invoke this C1, this line, and then it will invoke this line, and which is going to invoke itself. So then immediately the execution will come here, which is come back, and then if we run the continuation.run, we will get over here, not the top of this line, which is line number 12. So it will resume where it yielded. So that's the interesting thing. That's the interesting bit part. So if virtual thread gets suspended, the place it gets suspended, when it resume, it start from there. So that's the interesting bit. So if I run it, let's see the demo. So if I run it, you will see it calls start method over here, and then it executes this line, which is essentially C1, and then this line gets executed, so it yielded itself. The execution come here immediately, and then it calls the continuation.run again, and then so it is start printing the third line over here, which is this line, and then it's done. So essentially inside the virtual thread, that's what happens. Anyway, that's extreme high level point of view how it works. But yeah, there is a lot of documents available in inside.java. If you want to read about how virtual thread works, you will definitely be able to find tons of resources, tons of lectures. So go ahead and read them, and get familiar with them, because this is going to be amazing when this virtual threads is going to be a part of JDK. It's still part of JDK, but it's just under feature flag. And you have to enable preview. So it's not yet ready for production, but hopefully you can still use them, try out and figure out. And very soon we are going to be able to use them in production. I'm very excited. So that's the two side of city. So virtual threads is basically one city, and the rest of other is the other cities. Inside Project Loom, it's a brand new cities. We are not going to care about blocking call anymore. We're going to definitely the way we want to write code. If it's imperative, that's awesome. We can write our imperative code with virtual threads. And if it blocks, doesn't matter. It's cheap. We don't care. One thing though I have to put emphasis on, which is it's only take care of blocking calls. So if you have computation, don't run on virtual threads. So you will not get any benefit out of it. If you have a computational work that you want to parallelize, or you want to run in refined thread, use classical threads. That's where it shine. But you have, let's say you have a microservice that calls tons of other microservices to get result. Do use virtual threads, and you can write imperative code pretty interestingly. So yeah, so that's the highlight. So I have a few other slides which I'm going to skip over because we don't have time. So there some other languages have similar concept, which is coroutine in Kotlin, goroutine in Go, async wait in JavaScript, Python generator, Ruby fibers, and finally we have it in Java as well. So that's amazing. I'm sure people are going to be excited. I'm excited about this. Finally we have it, folks. So I'm gonna skip. There are tons of benefits of having virtual threads. Threads are cheap. We can do request per thread style, server-side programming. It becomes easy. So each request can handle by each virtual threads. So if let's say, for the sake of argument, if we have 1 million threads, we can create 1 million virtual threads, and our throughput immediately jump a lot, because with our traditional threading model, we cannot create millions of threads, right? But with virtual thread, we can. And in modern web applications, most of the time threads, spend time on I/O, which is essentially a blocking call. So that's a huge benefit. And we don't have to invest our time on reactive programming. So that's a good thing. And I don't know if it's a bad thing, but it's a good thing for me. I don't want to learn reactive programming because I am familiar with this tool set. So I'm happy. We can create millions of that. On blocking IO, virtual threads get automatically suspended. I already discussed about that. It support all these threading things, which is thread local, synchronization, thread interruption, all those things available. And Java code written in classic threads can be easily run in virtual threads. So that's a huge benefit. There are lots of other benefits. For example, we no longer need to maintain thread pool, no fine tuning. So that's a huge benefit. If you want to create executors, you want to create thread pools, you have to figure out a sweet spot, how many threads we want to create. That's a struggle. It takes a lot of time, takes a lot of hard work to find out the sweet spot. But with virtual threads, we no longer have to think about it. We can just create virtual thread whenever we need task per basis. So that's a huge saving. Anyway, there are lots of other benefits I'm going to skip over since we are at time. So in conclusion, we can say that's the two cities that I wanted to highlight, how they are treated in two different ways. And I'm excited about our new cities, which is Project Loom, where we're gonna treat blocking call is not our enemy. We are gonna embrace blocking call here. So that's the highlight. So thank you for having me and listening or watching these talks. That's all from me.
Thank you so much, Baslor. That was very interesting and entertaining and educational. I think we should leave it here. We're at the top of the hour, and we're on to the next J Champions Conference session. Thanks very much, Baslor.
Thank you very much. Thank you for having me as well. Take care. Bye-bye.